In this video, we look at several examples with probability. So Chapter 4 in your statistics textbook looks at Introduction to Probability. So this is the study of determining the likelihood of various events occurring. So we'll start with a game where we draw a deck from a standard deck of 52 cards. We have our 13 hearts, diamonds, spades, and clubs. So if I ask the question, what's the probability I draw an ace? Well, if we think about this, there's an ace of hearts, an ace of diamonds, an ace of spades, an ace of clubs. So there's 4 aces out of a total of 52 cards. So there's a 4 in 52 chance we randomly draw an ace. If you reduce that, that's 1 in 13, or a little over 7%. Now suppose I said, what's the probability I randomly select one card from the deck and it's not a spade? So again, I can think of how many cards in the deck are not spades. Well, there's 13 spades, which means the remaining 39 cards are hearts, diamonds, and clubs. So there's about a 3/4 chance that I draw something that's not a spade. The last one, suppose I draw 3 consecutive cards without replacing them. So here we have a sequence of events. And so remember this probability, in general, when we have a sequence of events, we multiply the probabilities as we go through that sequence. So the first card I draw, there would be a 13 in 52 chance it was a club. Now assuming that first card is a club, that means there's only 12 clubs left in the remaining 51 cards. So the probability the next one is a club would be 12 in 51. Again, the third card, if I've already drawn 2 clubs, there's only 11 clubs left out of 50 cards. So I multiply those probabilities and get about 1.29%. So pretty unlikely to draw 3 consecutive clubs. Second example, suppose we have a box or a bag with a bunch of marbles in it. 2 marbles are drawn without replacement. What's the probability that they're the same color? So if I think about this, I have red, blue, and yellow marbles. So one approach would be to think, what's the probability I draw 2 red ones? What's the probability I draw 2 blue ones? Or what's the probability I draw 2 yellow ones? So if I look at these individually, red, red. Well, using kind of the same logic as the previous example, probably the first one is red would be 6 out of 15. There's a total of 15 marbles in the bag, so the probability I draw one out and it's red is 6 in 15. Now, if I keep that marble out, what's the probability the next one is also red? Well, now there's only 14 marbles left in the box, and only 5 of them are red. Pull that out, now there's only 4 red ones left. I can do a similar argument for blue. There's 5 blue, 4, 3. Similar for yellow. There's 4 yellow, 3 yellow, 2 yellow. The idea being it's a sequence of events. So if I add all those up, I get the probability of 2 marbles of the same color is about 7.5%. Third example. Suppose a student is taking a multiple choice test and each question has 4 possible answers, A, B, C, or D, and only one is correct. If the student did not study and must guess, what are some probabilities? What would be the probability the student correctly guesses and gets them all correct? Well, again, I could think of this as a sequence of events. Probability of guessing and getting it correct is 1 in 4. Now notice here, the probabilities don't change, because if I'm just randomly guessing, each time I guess, there's a 1 in 4 chance I get it right. So 1/4 times 1/4, 5 times. Similarly, what would be the probability that I get all the questions wrong? Well, if there's 4 possible answers, 3 of the 4 are wrong. So the probability all wrong would be 3/4 times 3/4, 5 times. So about a 23% chance that we get the questions all wrong. Now, what's the probability I get at least one question correct? Well, if you think about it, that would mean I need 1 of the 5 correct, or 2 of the 5 questions correct, or 3 of the 5, or 4 of the 5, or all 5 of them. Well, a simpler way would be to think, what's the probability I get them all wrong, which I calculated in part B. So part B is the chance that we get all of them wrong, so at least one correct would have to be 1 minus that, because this is all the other cases where I get 1 or 2 or 3 or 4 or 5 correct. So about a 76% chance I'll get at least one of them correct. Last example, suppose we have a generic problem where we have the probability of A probability of A or B, and the probability of B complement. Suppose I asked what is A and B. So if you recall the addition rule for probability, it says that A or B is the probability of A plus the probability of B minus probability of A and B. So in this case, we don't have B, but we have B complement. If B complement is 39%, that would imply B has to be 61%. Because remember, B plus B complement has to add up to 1. So now if we plug all these numbers into the addition rule, A or B is 73%, A was 56, B was 61, minus A and B. So I can solve this equation for A and B, and I get the probability of A and B is 44%. Suppose I ask for the conditional probability of B given A. So this is the probability of B assuming A has already occurred. So recall our formula for conditional probability. Conditional probability is the probability of both events over the given. So in this case, the probability of A and B divided by the probability of A. So if I plug that in, I just calculated A and B was 44%. We know that A is 56%. So plugging in the probability of B given A is about 78%. If we continue this problem with one more, let's talk about independence and mutually exclusive. Are these events mutually exclusive or independent? So remember, mutually exclusive means the events cannot occur at the same time. Independent means knowing something about one event does not affect the other. Well, notice that A and B is not 0. Probability of A and B is 44%, which means A and B can occur at the same time. So they are not mutually exclusive. Also, remember that if A and B are independent, then the probability of A times the probability of B should equal the probability of A and B. Well, that's not true in this case. If you take A, 56%, times B, 61%, you do not get 44%. So A and B are not independent. You could also note on the previous slide that A given B given A was different than the probability of B, which means knowing something about A affects the probability of B. So these are not independent events.